Also, a warm welcome to everyone from my side. My name is Sebastian Petri, and I'm presenting today in my role as the responsible person for knowledge transfer between data science and domain or application, and especially in my case, it's diesel powertrain. The topic of the following slides, as already introduced, is condition-based monitoring aided by in-use data. And yes, first of all, I would like to start with a citation. So the term big data has come up a lot over the past years, and for us, it's really a term that we will have to handle. And in the end, this whole data is useless for us if we aren't able to extract information or, in the next step, insight out of this data. And so this citation I want to have here is to really picture that goal, that we need to transform data. And in the following slides, I will introduce the FEV approach, how we tackle this. So on our way in this transformation, we have a clear starting point where we collect all data from various sources. These can be sensors, transformations in calculation, or we have models. We have also logical information that we can gather, which then also is, first of all, data. And the challenges that we see here are that we have to select which data sources are the right ones and how we should handle those signals that are coming out. And this includes, for example, the pre-processing as well as filtering and, of course, the storage of data. Further, we need to define which kind of data services we want to implement or we want to provide. And we see here three major subgroups. First of all, informational, where we just give information about the system. We will also have the second subgroup, supporting systems, which can also give recommendations what to do. And in the third part, we have autonomous systems that fully react on the gathered data and try to adapt the system. And here we have the challenges, of course, how we can select suitable technologies to tackle these directions, and also how we can implement these into the system. So to achieve an efficient product in the end, in this case example, it's an expert system for powertrain. We need to have a close collaboration between all parties that are working on this. And this means that we have to bring data science on the table together with the domain and the application, and also all the physical fundamentals. And each of those fields provide a pillar in the whole system based on the data. And neglecting just one of those pillars will bring parts of the structure down, or can in the end break the whole project. So in this example here, the physical fundamentals provide the base principles. Then we have technical experts that define the operation range of the system. And then we can apply machine learning algorithms that can adapt the system, that can learn from the existing data and give additional information. And this whole blueprint of this construction, as I said, is just possible when we have a close collaboration between all parties involved. And that means also we need to have a common understanding and a clear organization who is responsible for what part of the process. So with this introduction, I'd like to come now to the condition monitoring that we have here worked on at FEV. And I would like to start with this first view on an embedded operation. What you can see on this picture is a fully onboard implemented system. That means we have, apart from the engine and the engine controller, we have also information coming from an onboard diagnostic system, similar to what we know from vehicles. And then on the upper left side, we have a condition-based monitoring system. This system can gather also information from the controller. We can have additional sensors. We can also get information from the diagnostic itself. and we are gathering this information, do pre-processing, and extract information about the condition of different components or the whole system. And then in the end, we will also have a user interface, a visualization that can provide this information to the operator. In this case, we have an informational subsystem. This monitoring system can be applied to different components of the whole powertrain. So for example, we have listed here the fuel system, lubrication, coolant, but also inside the engine itself, we have the pistons, the valves, bearings, and then of course the whole air path system, which can also be used to create a reference system by a model, to which we can then afterwards compare our measured signals to see if we have some misbehaving in one of the components. The idea of this concept is that we can predict and detect critical trends during the lifetime of the operation, and therefore we can afterwards react. To achieve this, as I said, we have implemented, for example, here for the air path, physical process model, which will model the whole path separated to components, which are based on our physical knowledge. And with this, we can have some kind of digital twin that is running on board to provide reference information about how the engine should behave. And this gives us the advantage that we can use this system right from the start of the first engine, because we are not depending on any field data. In the next steps, we can, what you see on the left side, use our hybrid modeling approach to even improve those models by training data models, which we can then decide to use in different operation conditions. And this decision is also being made by machine learning. On this slide, you can see a test case that we have set up for such a system. What we can see here is 3 different monitor types. On the upper part, we have the compressor monitor for steady state operation. The middle line is the turbine monitor for steady state operation. And in the lower part, we have the turbine monitor for dynamic operation. And in this specific test case, we have applied an offset on the turbocharger speed sensor, about 10%. And this means that we see that in the beginning, where we have a huge difference in the compressor pressure buildup, we can see that the monitor is not giving a past result until we really see the adaptation later in the system when the reference pressure and the measured pressure are similar to each other. In the second line, we have a continuous and constant deviation of 10%, which is here within our limits that we have defined, or within our threshold. So that means that our monitor will also give the result that he detects that it detects the deviation, but still it's within the boundary conditions. In the lower part, we are looking at the deviation in transient. So what we see here is accumulation of the deviation between the reference and the measured value. And as soon as we are reaching a threshold, the monitor will give out a failure result. In the next steps, we want to now go further from this pure informational system to a predictive maintenance system. That means that we are now also adding more intelligence to also create feedback from the system in terms of recommendations. So condition monitoring, as you see it in the lower part of this picture, is the analysis of the current situation, of the current condition. And this information will then be gathered within our field data. So we will get this information not only from one system, but we can gather from different systems. We can also gather from similar systems, and then store this on a database, perhaps in a cloud or on a server or whatever the infrastructure looks like. And then we have certain ways that we can follow. On the upper right side, this would be the way of predictive maintenance. That means we would use the gathered data to predict failure of components and recommend replacements and maintenance times. What we also try to use to do here is we would detect the root causes for this component failure to avoid maybe the same error in a similar system that it appears in under similar conditions. This insight also helps us to improve the development and production process. Because of this gathered data, we can also feed this directly back to the OEM or to the manufacturer of the engine. So he can or they can also implement this in their production process and learn for future generations or even for the same generation as a field fix. So we have learned starting the condition monitoring from the onboard system. We have now here the plant model and the engine monitors running on board, and we have just this reference system that gives us a deviation between measured and reference. In the next step, we go a bit further. We still have the monitoring running on board, but now the data analysis runs off board in a central computation facility, and we can also now consider data from the complete fleet. This data can then also be visualized through different front ends. For example, that could be a web interface for the fleet operator. In a third step, we would also implement now some prediction models. So here in this example, it's a digital twin that can run lifetime predictions, and then afterwards creates feedback to the fleet operation that maintenance or even adaptation of the controls might be necessary to bring the system or even a single system back into a good operation status. So the benefits from our solution is that we are tackling here at FEV the problems by having this close collaboration between data science and domain, as I also already mentioned in the beginning. And our objective is that we really understand data and data science, not only as a tool, but also as an asset to boost our developments here. And in this especially case, also the future large bore, because we see here a lot of potential. And by doing this, by having this close collaboration, we are targeting a sustainable concept that also helps to reduce development duration, that allows the scalability of our solution, and also the smooth integration or the transition into the production phase, so that we don't lose a lot of time by having to think about how to implement this. And this smart development helps us in the end to generate a smart product. And the solution here in this case is that we need to really focus on this interdisciplinary collaboration right from the beginning, because as you remember from this pillar diagram, if you neglect just one pillar, the whole project may collapse, and you have to really focus on the concept from the start on. And that also means that you have to really think from the start on how to transfer big data to smart data. And in the end, this also helps you then to select suitable technologies that you can apply. And yeah, again, for FEV, so FEV has years of engineering experience that we can now throw into this field, and we merged this together with our data science experience, and this will create, we call it best of two worlds or best of both worlds, and this will create the benefit from our approach. And as you can see here, we have also responsible people for each business unit that are really just working on the data transfer, the technology transfer between domain or application on the one hand, and data science on the other hand. And this strict definition of those roles allows us to be very flexible on the use cases. So coming to the end of this presentation, I want to again show you two citations. And in this case, I see there's a lot of potential because what we see is that a lot of big data collection is coming up in the last years, and this is a trend that is even proceeded further. And below 1% of this data is ever analyzed or used. So that means that over 99% of the data has no use so far. And this is something that we want to tackle to really get the most benefit and the most information out of this data. And as you can see, 90% of this data has been collected during the last 2 years. And we are expecting more to come in the next years. And to really have a smart solution, we need to focus on the selection of the correct data, filtering of data, and pre-processing of the data already on board of the vessels, on board on the vehicles, and at the sites itself, without having to transfer huge amounts of data. So that's so far from my side. Thank you.